This video is going to go over some basic concepts of enthalpy of reaction. So the first idea here is we have a reaction, methane plus 2 moles of oxygen react to form carbon dioxide and 2 moles of water. And you have a delta H there, which would be the enthalpy of this reaction. And on the right-hand side, you can see delta H1, negative 890 kilojoules, is shown where the reactants are at the top. They have higher enthalpy, and they fall back down to the products, which have lower enthalpy. The one on the top shown here is an exothermic reaction. Now what I want to call your attention to is the second reaction is the same reaction but in the reverse direction. So now we have carbon dioxide and water reacting to form methane and oxygen. And what you should notice is that the delta H for this reversed reaction is equal in magnitude and opposite in sign. And so you know that it's going to be positive 890 kilojoules, and that should make sense for a couple of reasons. One is that if the first reaction releases 890 kilojoules of heat, then in order to get the opposite reaction to occur, you must have to put in that same amount of heat in order to get it to occur. And if you look at the enthalpy diagram on the right-hand side, it should make sense that if what was once the reactant at the top is now the product, then the arrow is just going in the opposite direction, and now we have an endothermic reaction that requires 890 kilojoules. So this is a concept that you will use over and over again. If you reverse a reaction, then that reversed reaction has the same magnitude, meaning absolute value, but the opposite sign. So if it was once negative, it becomes positive, and vice versa. Now, the next idea I want to explain to you before we do some practice problems is here we have 2 moles of ethane reacting with 7 moles of oxygen to form 4 moles of carbon dioxide and 6 moles of water. So this is combustion of ethane. And you can see here there's a delta H of a reaction given there. The degree symbol at the top after the H refers to standard thermodynamic conditions. That would be 298 Kelvin temperature or 25 degrees Celsius. And a pressure, we usually use the pressure of 1 atmosphere in general chemistry. And there are a few other stipulations that we'll talk about later. So what you see there, that negative 3,119.6 kilojoules, that means that if this reaction occurred exactly as it is written, and you had 2 moles of ethane combusting, then you would see the release of 3,119.6 kilojoules of heat. So this describes the reaction exactly as it is written. 2 moles of ethane reacting with 7 moles of oxygen, etc., etc., etc. And we'll do some calculations later that will explain this to you, but you're not typically in a problem going to be given exactly 2 moles of ethane. You might be given 1 mole, or maybe it'll be 0.5 moles, or maybe it'll be 1 gram, and you'll have to figure out what is the heat released with a different amount. So keep in mind that when you have delta H provided here, and it's just listed as kilojoules next to the reaction, it is describing the reaction exactly as it is written. Now, alternatively, sometimes you see delta H's and they have units of kilojoules per mole. So another way this value could have been provided is a heat of reaction, which is another, it's like a slang term for delta H of reaction. Heats of reaction can be alternatively given in kilojoules per mole. So for example, this problem might have listed the delta H of combustion for ethane is negative 1,559.8 kilojoules per mole. Now you can see this is half as much because the one given at the top is for 2 moles combusting, and this is per 1 mole. And so you would know which one is which because in the top example there's no moles given, it's just kilojoules, it's not kilojoules per mole. In the bottom example, it's in kilojoules per mole. Since this is a combustion reaction, it's ethane that you have 1 mole of. Sometimes it's not that obvious, but usually it is. So we're going to do some practice problems to make sure this makes sense. And those are shown here. So problem number 1, we have a reaction and it has a delta H written next to it. And because that delta H is in kilojoules and not kilojoules per mole, and we see stoichiometric coefficients in the problem, right? 4 moles of iron, 3 moles of oxygen, 2 moles of iron oxide. That means that the delta H that's written there pertains to the reaction as it is written, which means that 1,652 kilojoules of heat would be released to the surroundings whenever 4 moles of iron reacts with 3 moles of oxygen and forms 2 moles of iron 3 oxide. Now in this problem, we're asked to calculate the heat released. So it already stipulates, it knows that heat is being released, which is true because this is an exothermic reaction. Calculate the heat released. So this is going to be a positive value because it's asking for the heat released. It's not asking for the heat associated with the reaction. It's asking for the heat released when 5 grams of iron oxide is produced. So we need to take that 5 grams and convert it into moles and then figure out what the heat is associated with that many moles. We know the amount of heat that's released when 2 moles form, right? That's the value given up there. 1652 kilojoules are released when 2 moles form. So let's instead convert that 5 grams into moles. So that's saying that that's the value for the reaction that's provided, which forms 2 moles. So we're going to take our 5 grams and figure out how many moles that is. It's definitely less than 1 because this is going to be a heavy molecule. So iron is 55.85, that's here. Multiply that by 2, 16 times 3, and you get 159.7. So 5 grams is the same thing as 0.0313, so 3/100ths of a mole. So the heat that's associated with the formation of 0.03 moles is going to be far less than 1652, right? Because that's 2 moles, and this is a much smaller number. This is almost 100 times smaller, but not quite. And so you can kind of guess. You can kind of say, well, I know it's going to be between 165, that's what it would be for 2/10ths of a mole, 0.2. And if it were 0.02, right, instead of 165, it would be 16 kilojoules, right? So you know that it'll be between 16 and 165, okay? So you can kind of guesstimate a little bit. So the heat, delta H that's given there, 1652, that number is for 2 moles. And so you're going to write that down, 1652 kilojoules per 2 moles that form. And you're going to multiply that by the number of moles that you actually have to get the actual heat that is required. So we multiply these together and you get 25.86. Because it says calculate the heat released, I'm sorry, I said required, calculate the heat released, you're just going to make it positive. And it has, looks like it needs 3 sig figs because we have 5.00, so we're going to have 25.9 kilojoules. It's positive because it says it's being released. It knows the direction. Part B, determine the change in enthalpy associated with the following reaction. So first what we need to do is we need to compare these two reactions to each other. So you're given this information, 4 moles of iron, 3 moles of oxygen form 2 moles of iron oxide, and that has this as corresponding delta H. So how does this second reaction under Part B compare to the reaction in Part A? There are 2 differences, okay? So take a look at it for a minute and let me know what you think about those 2 differences. One difference is that this new reaction is the first reaction in the reverse direction, right? So what were once products, iron oxide, is now the reactant. So this is now the decomposition reaction of iron oxide. There's a second difference. Now with this first reverse reaction, that means that we're going to change the sign of delta H. So if we simply reverse the reaction and we have 2 moles of iron oxide forming 4 moles of iron and 3 moles of oxygen, that would be positive 1652 kilojoules. So you reverse the reaction, you change the sign of delta H. The other difference, however, is that this is also multiplied by 2. So we're going to take delta H and we're going to multiply that by 2. So our new delta H is 3304 kilojoules. And that's the answer to Part B. Number 2, we have combustion, and we're given a heat of combustion of liquid propanol. Calculate the heat associated with the combustion of 10 grams of propanol. So here, instead of saying heat required or heat released, it tells you heat associated, which means you need the sign in there, okay? So it gives you the heat of combustion, which is the reaction shown, and it is negative, which means that it is an exothermic reaction, which means the heat associated with that combustion will also be negative. So here we know that the heat of combustion of liquid propanol is negative 2020 kilojoules per 1 mole of propanol. So not as the reaction is written with 2 moles, but per 1 mole. So it's already been converted into kilojoules per mole for us. Calculate. So we have 10 grams of propanol. We need to convert that into moles. And that's just saying that it's per mole. So we're going to convert 10 grams, figure out how many moles that represents, divide by the molecular weight, and that gives us 0.166. So it is, it's a little more than 10 times less than 1 mole, right? So we know it's going to be somewhat bigger than 202, than negative 202, right? It'll be a little bit larger in magnitude than that. So we take our 2020 kilojoules per 1 mole, we multiply by 0.1664 moles, and that's going to give us the value of Q associated with this reaction, which is negative 336.14. I'm going to round that to 3 significant digits. That's going to be negative 336 kilojoules, and that's going to be our answer.